Hello everyone, welcome you to this video lecture. Here I discuss lab number 7 where we did actually transient analysis for second order system. So as you know that we have this generalized second order system is represented as a transfunction that b divided by s square plus as plus b. Now we have four possible responses. One is overdamped, underdamped, undamped, and critical damped. So the main idea is these responses based on the pole locations. If you have two real poles but they are unequal, then we have overdamped system. If you have a complex poles, we call it underdamped. Undamped, we have imaginary poles, and we have a critical poles if we have two repeated real poles. Now let's start with task 1. We have to identify the type of system with the help of pole location. So we have two systems and we have to fill this table with pole location and type of response. So let me open the MATLAB. So first of all we start with task 1. So before starting this, so you have to open a script file where you start with close all, clear all, and then clear the command window. So when you run these three commands, it will close all the data and your workspace is clear. Now we start with task 1. For task 1 we have to define s so that we can enter trans function. So we enter g1 as 400 divided by s square plus 12s plus 400. Similarly g2 is 625 divided by s square plus 625. So to calculate the pole location we use pzmap command in MATLAB. pzmap of g1 for pole 1 and 0 1, and similarly for second. Now we use the display pole location and use display to do it. So this is your task 1. If I just run this, I will get the desired result in the my command window. So look here, first two poles is for g1 and second two is for g2. Now if you look at the first system, it is actually has a complex pole, so this means that this is an underdamped system. Now for second one we have imaginary poles, so this means that this is an undamped system. Now if we move to back to our lab task, so the lab task next one is task 2 is about the transient response in steady state. So I will directly go to the task, and here we have to calculate the second property of signal system that related to the rise time, overshoot, peak time, and settling time. So you already know the theory, so I just go through the task. So here we have a closed loop block diagram where we have an input RFS, output CFS, and this is the block diagram. So first we have to calculate this feedback, then multiply with k and again feedback. So this gives us the system. Now here the task is interesting one is that to find the value of k for which rise time is 1 second. So this is actually a first lab towards the control design. Here we have to find out the gain, but we do it using hit and try method. So the first task is to find the k for which the rise time is 1 second. Second task is to find the k for which settling time is 5 seconds, and last one is find the value of k for which the overshoot is 15%. So for this task we have to find these k's for these three scenarios. So actually we have to design the controller, gain controller, which can satisfy these specifications, which is rise time, settling time, and overshoots. Now for this task, if I go back to my MATLAB script file, so I start with task 2 here. So look here, first of all I write the S1, that is 1 over S into S plus 2 into S plus 3. If I go back to my lab, so I write this as system 1, this as system 2, then I solve the whole system. Okay, now look here, the script, so I call this as a system 1, then this is system 2, then I take the feedback to get system 3. Now for gain of rise time I write it kr equal to 0, k is 0, k overshoot is 0. Now I have to write a loop so that I have to find the gain. I don't know, so I start a loop for k from 1 with an interval of zero point 0.1 to 100. So I first of all have to write the system. That system is the feedback of k time s3 comma 1. S3 is the other closed loop. S3 is this one. Okay. Now I take the closed loop, lost closed loop with k. Now vary this k from actually 1 to 100 so that I can calculate the values of k. Now for that case, what I did actually, I use step info, a command which is available. So step info is give you a structure. I take that structure into info part, and then I use the condition for part 1 that if info dot rise time is greater than 0.99 and info dot rise time is less than 1.01. So question was about 1. Actually, this is not necessary that we can get 1. I don't know the range, so I take an interval so that I get approximate, very close result to that. So if this condition satisfy, I get the k where I satisfy the rise time. Similarly, I did it for settling time, but here I get 4.9 and 5.05. So here I can use this to calculate the settling time. For overshoot again, overshoot was 15%, so I take a range of 14.9 to overshoot of 15.5. So you have to remember this thing. You have to write this very same with capital S and capital T. Otherwise, you get an error. So you have to write the same variable name as available in info. Now I just close this and then I display the result. How I do that, I just say display k values, then display the first one and so on. Now if I run this one, I will get my result. Now I resume it, and you see that we have k values that come out after this very simple coding. Is for first part is 9.5, 5.7, and 7.1. Now I will move to the last part, that is the last one, which says that to look at the damping and natural phenomenon. So if we look at, there are three main properties. We have type of response, then we have timing, and then we have a look at the how damping ratio behaves. So in that case, task 3 is that this is the system where omega n is, if we look at this 16, so omega n is 4, so we have to vary the zeta from 0 to 1.2 and look at the pole location on PZ map and also step response, how it behaves. So for this last task, how I do that, I again this is the last task where I have to change the zeta from 0 to 1.2. If you know that when zeta is 0, so this means that your system is oscillatory or undamped system. When zeta is 1, this means that you have a critical damp. When zeta is between 0 and 1 is underdamped, and greater than 1 is overdamped. So here you get all type of responses. Okay, so what I did, I for this task I start with omega n equal to 4, then figure, then zeta variations. This is the system. Then use PZ map and hold on. So for first case, I just run this script and it will give me the PZ map. So look here. So if I start from here, okay, so this means that this is the point where we have a damping is 0. Now when I came here, damping is 1. So this means that when I increase the damping from 0 to 1, I will move towards the real axis. Okay, when it is increased, I will go, one pole go in this direction, other pole go in that direction where we have overdamped response. So here if we have critical damp, this is underdamped response. So this is the first one where we get the analysis. For second one, We have to look at the step response. That is a bit not clear here, but if I look here, so we get a figure. It is a bit confusing because we have oscillatory response, so this type of response we get. So this is the main idea about this lab, so you can do it yourself. Thank you. I will stop here. Thanks.